Now let's learn about linked lists, which have a lot of overlap with arrays, but also a lot of differences. The first thing to know about linked lists is that they are made up of list nodes, or sometimes just called nodes for short. A list node is an object that encapsulates two things at a minimum. These are the value of the list node. It could be an integer, a character, it could be another object, it could be anything. Maybe in this case, we have a 4 as the value. And also we have next, which is a pointer. This is going to tell us what is the next list node in the linked list. So this is essentially a way of connecting multiple list nodes together, which forms a linked list. If we just had a single list node, it wouldn't be very useful. In this case, let's say our next pointer points at null, which is another way of saying that it points at nothing. That means that in this case, we just have a single list node. That's not very interesting, so now let's understand how these nodes can be connected together. Let's first build a linked list. So first I'm going to create one list node. The value I'm going to give it in this case is going to be a string. Let's call it red. And the next pointer is initially going to be empty, or we could say it's by default set to null, so it's not pointing at anything. That means this list node is not connected to anybody yet. And we know when we create this object, it's going to go somewhere in memory. We don't necessarily get to control where it is, but we know it's going to be somewhere. We know that we're going to have a red node somewhere in memory, and it's not going to be pointing at any other node yet. Next, we'll create a couple more nodes, let's say a blue node and a green node. So now that we have 3 list nodes, it's time to actually connect them together. Now, in most languages, the next pointer is actually a reference to another list node. That's how it's implemented. So in terms of code, this is what we could do. We could set list node 1, assuming that's the name of our variable, our object that we created, dot next, the next pointer, to be list node 2. So what that would do is take this pointer and basically tell it that the next node in the list is going to be this node. Now, what's actually happening under the hood at the lowest level is we have some address for our second list node, our blue list node. Let's call it XX. And maybe this one is stored at address YY. The way we know how to get to the second node is at the lowest level. Maybe your language or operating system is doing this. The pointer tells it that the address is here, so that's how we know how to get to the second node. But usually, depending on the language that you're using, you don't have to worry so much about the address because the reference to that object is enough. So when we talk about pointers, we're usually talking about references to objects. But I'm mentioning this because as you can see here, the nodes are out of order in the way that we're going to connect them. We've connected our red node to our blue node, but the order in actual memory is the opposite. What this means is that linked lists are not stored in memory the same way that we use them as programmers. They could be in some random order in memory, but they're connected via pointers. So the red node is going to point at the blue node, and eventually we're going to have the blue node point at the green node. We could have some big mess like this in memory, but as programmers, we're going to have something nice and clean like this. So this is a difference from a linked lists compared to arrays. Arrays are stored the same way in memory, but linked lists, as we can see, are not necessarily stored the same in memory. Next, for us to connect list node 2 to list node 3, we would do the same thing we have down here, except for list node 2 dot next, we would have a 2 here, is going to be set to list node 3. So something like this. And then we would have a nice linked list finally formed like this. So now that we have an idea of how linked lists are stored in memory, we're not going to worry so much on the details of what's exactly going on under the hood. Now, what if we wanted to start at the beginning of our linked list and then loop through every single node until we got to the end? And we would know we got to the end, by the way, because our last pointer is not pointing at anything. Now, depending on the language that you're using, the code for that would look something like this, where first we have a variable called cur. We initialize it to be at the first node in the linked list. And we keep looping as long as our pointer current is not pointing at null. What that means is we have a valid linked list node. So let's walk through this code really quickly. Suppose this is our current pointer. It's pointing at the red node. That's how it's initialized. Then we go to the while loop statement. Right now it's not pointing at null. So then we're going to enter the while loop. Current is going to be set to next. So we're going to follow our next pointer over here, which is now going to be pointing at the next node. Very simple. Then we're going to go back to our conditional. Current is still not equal to null, so now let's set it to current.next. So we're going to follow the next pointer, which is now pointing at the green node. So this is where our current pointer is now going to be. We're going to again check the condition. It's still not equal to null. So now we're going to follow the next pointer again, which in this case, it is pointing at null. It's not pointing at any other node. So now our current pointer is going to be set to null, and then we're going to execute the conditional. And in this case, it's going to be false. So we're going to no longer execute the while loop, and we're done with that piece of code. Now, my question for you is, what would have happened instead if this next pointer of the third node was actually pointing at the first node? Well, we would have started here, then went to the blue node, then went to the green node, and then we would have came back to the red node, and then back to the blue node, back to the green node, and just kept doing that over and over again. It wouldn't be very fun to run because the program would crash. It's an infinite loop. But going back to the first case where we didn't have an infinite loop, what was the time complexity of going through the entire linked list? Well, it was the same as doing so with an array. It was big O of n, where n is the size of our linked list. So far, we've learned that linked lists are pretty similar to arrays. Let's talk about a few more similarities real quick. As programmers, it would probably be helpful if, as part of our implementation of the linked list, we're always keeping track of the head of the linked list and the tail of the linked list, or the end of it. So let's assume that we always have pointers that can give us access to the first element and the last element. If we have a linked list of size 1, suppose these didn't even exist, that means our tail pointer would be pointing at the same element as our head pointer. That's how we would know we only have a linked list of size 1. But in this case, we have a couple more nodes. Suppose we now wanted to add a new element to the end of the linked list. And let's say we create a new node and its value is purple. Well, if we want to insert it at the end conveniently, we have a tail pointer at the end of our current linked list, and all we need to do to add this to our linked list is just connect the pointer. So we would simply take the tail.next pointer and set it to list node 4, which is our purple node. So that would look something like taking this pointer and then instead connecting it to this one. But the problem here is that our tail is still pointing at the third node. We want to update our tail pointer now to actually be pointing at this one. And in terms of code, that's also pretty easy. We can set tail equal to list node 4. We could also have set tail equal to tail.next, because remember, tail is still pointing at the third node, and we know tail.next now is set to list node 4. So by setting tail equal to tail.next, we're automatically setting it to this node. Can you tell me the time complexity of this operation? Well, it was a constant time operation. Since we already had a tail pointer at the last node, we didn't have to iterate through every single element in the linked list. We started all the way at the end, and then we created a new node and then connected the pointers. It was just one operation that we needed to do, which is the exact same thing with an array. Now let's say instead we wanted to remove a node. Removing any node in a linked list, whether we're talking about the end of it or the beginning of it, is also always a constant time operation. But there's a really big caveat. That's assuming we have a pointer to the previous node that we're trying to remove. So if we're trying to remove this node, we should hopefully have a pointer to the previous node. So if we're removing this node, what we would do is set our head.next pointer. Instead of it pointing at the second node, we would set it to the next node that it's pointing to. So this is a little complicated because we're chaining the fields. Head.next, remember, refers to this node. This node is equal to head.next. And then if we say .next one more time, we're following this pointer to the third node. So what we know is this evaluates to the third node. So when we say head.next, which is this pointer, is pointing at the third node, we're basically getting rid of this guy and taking this and setting it to the third node. Now, if we want to, we can free the memory that this node was taking up, but in most languages we have garbage collection, so we don't really need to take care of that. The language and operating system will take care of that for us. We can assume that it no longer exists if there aren't any pointers pointing at it anymore. But this is sort of a benefit compared to arrays. We can remove any element from whether we're talking about the beginning or the end in constant time because we don't have to shift everything over like we did with an array. But in the general case, if we wanted to, let's say, delete an arbitrary element in the linked list, we would first have to start at the beginning of the linked list and then follow the pointers until we found the element and then remove it. So practically speaking, to remove an element, it can still take big O of n time if we have to search for the element.